Welcome. Today I'm going to talk to you guys about claims and evidence and how they work in physics in particular and in science in general. If somebody were to come up to you and ask you what let's say a teacher does in one sentence, you probably could come up with a pretty good definition of what a teacher does. You could probably do the same thing for professions like doctors and historians, engineers, construction workers, janitors, all sorts of different careers. But when it comes to a scientist, I think people would struggle a little bit more with coming up with one good summary sentence. And so I'd like to give you mine if I could, because it's relevant to what we're talking about today. Uh, a scientist takes observations of the universe, or one part of the universe, makes a claim about that, trying to explain it, and then looks for evidence to support that claim. That's exactly what I would say a scientist does. And so that's what we're going to talk about today, is the importance of claims and evidence and how you might judge whether it's a good claim and whether it's good evidence. So we're going to use this basically throughout the rest of the year. So it's something that you want to kind of get a grasp on at this point and practice it throughout the rest of the year. I'm going to slide myself off to the side here. And I want to sort of officially welcome you to video 002, Claims and Evidence. We move on to the first slide, which says what makes a claim scientific. Now, this is a kind of an important one, particularly for me, because I personally sort of tread the line between science and non-science. I don't know if you know this, but I was actually trained in undergrad as a historian. I took a lot of physics and a lot of calculus classes, but my main focus was on World War II history. And oftentimes people will say to me when they find out that I studied World War II history, I think that the Germans would have won World War II if they had just invaded England with ground troops, which they didn't do. Now, this is a claim, right? I think that this would have happened if that had happened. It's a claim, but it's not what I would call a scientific claim. And so I want to talk to you just briefly about what makes a claim scientific. First off, what is a claim? So a claim is some attempt to explain things. So it's an explanation. So don't get confused by that. What you might, explanation, there we go. You might get confused by this word right here, because in elementary school and in middle school, your teachers told you it has to be a if, and then one variable, then another variable statement. And that's simply not the way science is done. It's a convenient way for disorganized and somewhat confused and not very worldly elementary and middle school students to be able to do things. But that's not really how scientists do things. They make a claim that gives a good explanation of things. And then that explanation has certain implications. So it implies one thing, let's say an implication number 1, and another thing, implication number 2, and a third thing, implication number 3. So it makes these implications, this explanation. Let's give an example here. So at one point there was a claim that was made that DNA is the map of hereditary information for cells. So that's a claim, it's an explanation. How do cells pass on hereditary information? They pass it on through their DNA. So that explanation then has some implications. Number 1, you could say one of the implications would be if there's damage to DNA, then a cell may not be functional. Another implication might be that DNA must then be able to be translated into some other usable form of chemical, and that's where we get proteins from, right? And then there might be a third implication. You get the idea. So what we could do then is we could take each of these implications and then try to test them. And that's where we come up with the idea of what a scientific claim is. A scientific claim is one that ends up with tests that will tell us whether the implications are correct, and by argument then whether the explanation itself is correct. If you could damage DNA and it wouldn't harm the daughter cell that was created, the daughter cell was just exactly the same as it would be if it didn't have harmed DNA, then you might have to change your explanation, your claim. Your claim might be refuted, or you might need to modify it to take that new information into account. So the testing part is what makes the claim scientific. This is, again, this is what makes it scientific. So I'm going back to my claim about Nazi Germany. Would the Nazis have won World War II, at least in Europe, if they hadn't invaded England with ground troops? And the answer for that is, how am I going to test that? I have no idea. I can make computer models, but think about all of the different variables that you would have to take into account if you were going to try to test it with a computer model. You would have to have a ridiculous number of variables taken into account, really far too many for you to do an accurate modeling of it. It's much like people try to predict the weather now. You can try to predict the weather, but there's really a lot of variables that go into it. And so computer models do their best, but they're not 100% accurate. And I would argue that a computer model of the weather is probably easier than a computer model of what might happen in if some hypothetical action in a war. So it has to be scientific. It has to be something that we can test. If it can't be tested, in other words, if it can't be proven wrong, then it's not really scientific and it has no place in physics. So we want to make sure that we take that into account. Again, a claim is similar to a hypothesis. A hypothesis really should be an explanation that has implications, but the elementary and middle school teachers who taught you about that word really, I think, used it in a kind of an inappropriate way. It was good for the time, but now you're more sophisticated and more worldly and have more experience. And so you can learn that what the real words should be. Okay, so we're going to move on to the next slide. Now, once we have a claim and we know what the implications would be, we should be able to come up with evidence. And that evidence is made up of facts. And so this is our key word right here, facts, which is something that a word that you use all the time probably. But for scientists, it has kind of a specific meaning. So they're observations or measurements, maybe, that are agreed upon by many trained observers. I put in trained here because I want to make sure that you understand that evidence can be good and it can be usable, but it has to follow or meet certain criteria. And so here's the criteria for good evidence. Good evidence, there we go, evidence has to meet 4 criteria. Okay, so number 1, the first thing is it has to be valid. So by that I mean it has to be true, and it has to be gathered using acceptable methods. What do I mean by that? I mean it has to be gathered using methods that any trained observer might use with acceptable methods. So again, you have to use correct lab techniques. You have to have those techniques judged by other peers, by other scientists, and have them decide that you did a good job, you did it the right way. Gathered with accepted techniques and methods. Excellent. And this is where, this is where the idea of a peer-reviewed journal comes in. The scientists have to publish their facts and their claims in a journal which is reviewed by other scientists. And the reason they have to do that is to have those scientists judge whether that evidence is good. The first thing they do then is look at how the evidence was collected and whether or not that evidence is true. So that's why we do it, because we want to make sure to check to make sure scientists aren't making random claims with evidence that they've made up or used improper techniques to find. The second is it has to be repeatable. So once it's not enough that I go in and read a journal and say, okay, it looks like this is how they did it. That's exactly how I would have done it if I had decided to do that experiment. Then I have to be able to take that same method and use exactly the same procedure and materials and then get the same results. So it has to be repeatable by other people, typically often. It has to be repeatable many times before people will believe it. So you have to be able to find those same facts using the same types of measurements and methods over and over and over again before we can judge whether it's good evidence. Finally, this is the third piece, and then there's one fourth one, but I'll talk about that now. It's a little different in a second. It has to be relevant. So what I mean by that, and I have to be honest with you, relevant is one of those words that I always have to think about for how to spell it. So it has to be relevant. Relevant means it has to relate back to what you're trying to do. So in this case, it has to actually support the claim that you're trying to make. Or in this case, it has to actually test the implication of that claim that it says it's testing. You might be surprised how often this comes up as a problem. So it has to be relevant to the claim. There is a fourth piece, and that fourth piece has to do not with each individual fact, but with all of the facts together. And that is the body of evidence that is produced, is that thorough enough? Is it thorough? So is the implication thoroughly supported, and therefore the claim thoroughly supported? So before I am going to believe anything that I hear someone claim, I'm going to have to ask for a thorough amount of evidence. So those are the four decisions that you have to make when you're looking at evidence. They're also the four things that you should think about when you are trying to gather your own evidence, particularly these two right here, those two right there. Is what I'm measuring actually repeatable? Are other people going to measure the same things if they're doing the same methods and using the same tools? And am I actually testing and supporting the thing that I think I'm testing and supporting? Those are the two things that I want you to kind of focus on for this year. Okay, last slide. So I want to give you an example here. And I'm going to use this example. I'm going to slide myself out of the way there. So I want to use this example, which is a little controversial because it does conflict with some religious points of view. So I want to just put this out there. This is an example of a scientific claim, and I'm going to show you what the evidence is to support that claim. I'm not in any way saying you must believe it. I'm saying that typically physicists do believe this, and they believe it for the reasons that I'm going to talk about in just a minute. But it is a scientific claim, and it is supported by evidence. It's also one of the examples that people come up with when they try to talk about scientific claims that in no way could be supported by evidence, but in fact are. So I want to just take a minute to talk about this. There is a claim, or was a claim in the 1900s, middle of the 1900s, that the universe at one time was all compressed, both the energy and the matter and the space and the time were all compressed into a very small volume. And then, for reasons we don't understand, an event occurred in which that space and time began to expand outward. And with it, the energy that was bound up in that tiny little space began to expand outward as well. We call that a Big Bang-like event. I use the the phrase Big Bang like, because it's now sort of debated as to whether it was actually exactly a Big Bang or something very close to similar to what they're talking about in the 1900s. Anyway, so this was predicted to have happened a long time ago, 13 plus billion years ago, 13.8 if I remember correctly, billion years ago. So you might think, and many people do, there's no possible way you could get evidence that would support this claim. But in fact, we actually have quite a bit of evidence that supports the claim. You just have to look not for the claim itself, but what it would imply. So the claim was that there's this Big Bang-like event. At the time of the Big Bang, all of the energy had roughly the same temperature. And it was kind of evenly distributed, so the claim goes, evenly distributed in that little space. As it expanded outward, we found that there might be an implication that goes something like this. If we look around the universe, we see that objects are moving away from us. So in the 1920s, a man named Hubble found that galaxies, for the most part, are moving away from us. And the farther they are from us, the faster they're moving away from us. Now that would only be true if, number one, we were at the very center of the universe, which doesn't seem to make a lot of sense since we're not even at the center of our own galaxy. And number two, it would happen if everything in the universe was moving away from everything else, like two dots that you draw on the surface of a balloon as you blow it up. Those two dots move apart from each other, but they're not really in the center of the balloon. There's really nothing in the center of the balloon. So that's one piece of evidence that could be used to support a Big Bang-like event. The second one is the amount of hydrogen and helium that we find in the universe tends to agree with the idea that at some point after the Big Bang, we started to get objects or energy cooling off enough that it could start to form matter. It could start to condense down into matter. And so we predict using mathematical models at what temperature those particles would start to condense down. So we'd start to get electrons and neutrons. And those neutrons then would degrade into protons. And once you have neutrons and protons and electrons, you can start to build atoms. And of course, the simplest type of atom is a hydrogen atom. And so as we look around the universe, we see that the universe is predominantly made up of hydrogen atoms. And it just so happens that it matches pretty well with what we predicted would happen if there were a Big Bang. So that's our second piece of evidence. Again, it's testing an implication made by the claim of the Big Bang. The implication is that matter would cool down and condense into the simplest possible atoms first. Next, this is the cosmic background radiation. So this is a map of the entire universe looked around in microwaves. And what we find is that the entire universe looks pretty uniform. Now you see there's little dots and such around here, but these are variations of fractions of a degree Celsius as we look at the temperature of the surrounding universe. So these are very small variations in temperature. Now, it seems strange that the temperature of the universe would be almost exactly the same no matter what direction we look. The implication by the Big Bang was that it started out that all parts of the energy that was in the Big Bang had the same temperature. And so one of the implications would be that it would be roughly the same temperature now, even 13.8 billion years later, and even after it had cooled down quite a bit. So that is in fact what we see. And then finally, if you take that temperature right there for the surrounding universe and you map it out, it predicts exactly with what we would use mathematically to determine how cool the universe should be after a Big Bang that occurred about 13.8 billion years ago. So we find that it should be a certain temperature. The temperature predicted was this black line curve right here, right there. And so this is the radiation that we find, and this is the intensity of that radiation. And this is what a radiation curve would look like for the temperature that we predict the universe to be. And look at each of these little lines right here is the data that we've collected, the facts that we've collected about the universe when we look at different wavelengths and try to measure their temperature and their intensity. And it looks like it follows exactly on the line that we predicted. And so in the end, the Big Bang claim became the Big Bang theory, a way to explain the beginning of the universe that is well supported by multiple strands of evidence, by facts from all sorts of different types of evidence. Again, if you disagree with that religiously, that's okay. I'm not trying to convince you otherwise. I'm just showing you how a claim has implications, and then those implications then are tested using facts and evidence. Okay, so we're done. Took a little bit longer than I thought. Normally videos like this are not going to take this long. So I just wanted to point that out to you. This is about 21 minutes at this point. I'm going to try as hard as I can to keep each of these videos around 10 minutes. This is an important one, and it's one that we're going to talk about throughout the course of the year. Claims and evidence are going to come up quite a bit. So I want to make sure that you have a pretty thorough background on it. If you have questions on it, let me know. I will try to explain as best I can. So thanks for watching. Don't forget to fill out your note sheet for this. That needs to be submitted, and then you should also have a question form as well. Some possible questions might be some questions about other types of claims, some questions about claims themselves, or some questions about the Big Bang theory as it stands today. I will do my best to try to answer those. All right, there we go. Thanks for watching. If you have any questions, let me know. Again, we're going to be talking about this tomorrow, so make sure you get all that stuff submitted. Thanks for watching.